So that's a neat little example, again, with some central angle and also with some inscribed angle work, but now we're kind of looking at some distances. So let's take a read of what we have here and see what we can do. Point C is at the center of a circle, and it has a diameter AB equaling 10 centimeters, and a chord BD equaling 6 centimeters. Now, we could kind of say, oh, we got a diameter. We can, of course, give a radius as well, but that's not actually going to help us in this question. We're going to have to take a look at the measure of angle ADB. It's kind of like a hint in the question. Now, as much as you might be inclined to say, oh, that's definitely 90 degrees because it looks like a 90 degrees, try to temper yourself just a little bit here. I want to take a look at a diameter here, and since this is a straight line, we know that this diameter and this arc is going to subtend 180 degrees. This angle going across from angle BCA is 180 degrees, which means that the inscribed angle ADB, that subtends the same arc AB, which is this 180 degrees here, has to be half of that, equals 1/2 multiplied by 180 degrees, or just 180 degrees divided by 2. For this reason, it's 90 degrees, not because it looks like a 90 degree angle, but because, well, it actually is 90 degrees because it subtends the same arc that the central angle ACA or BCA does, which is 180 degrees. So kind of an interesting thing that we can do here is 180 divided by 2, which of course equals 90. So that's kind of like our explanation of the reasoning there. B, what is the length of chord AD? Justify your answer. For these types of questions, I kind of like to write down what we're looking at rather than just kind of doing it on the page itself. So I'm going to write down what our triangle sort of looks like here, and I'm going to label it out as A is over here, B is over here, and D is over here. You have to spatially kind of think a little bit. This is going to be C as well. Not really important, but there's C. And just kind of reorient this in the way that we're kind of used to looking at these triangles for. BA is our diameter, that's 10. Chord BD is going to be 6, and that means that we can solve for DA using Pythagorean theory. So we know Pythagoras theory by now. C squared equals A squared plus B squared, where our hypotenuse is always going to be across from the 90 degrees, so that's our 10. So we're going to put 10 squared into where C is. I'm just going to say 6 is going to be our A. You could say B as well if you wanted to. 100 equals 36 plus B squared. And you can do this question in a number of different ways. If you'd like to just think about, oh, what number can I square to make up the excess to get to 100? You should kind of get into the habit of looking at this one and saying, well, what do I have to do to get to 100? And there is only a couple things that you can add to this to equal 100. But in this case, I'm just going to subtract 36 from both sides since we've kind of dealt with this type of a unit before. Kind of like in our linear inequalities or linear equations unit. So 100 subtract 36 here, just kind of isolating for it. We're going to get 64 is equal to B squared. And you should know that your perfect squares means that 8 has to equal to B. So our length of the chord AD must be equal to 8, and we're going to put on centimeters on the back of it. So kind of an interesting little question here to do. Deals with central angles and inscribed angles, but then we're also going to deal with some distances as well. Short little work just using Pythagorean theory, and we're done.